Hello, in this video we're going to have a look at scientific notation. So a number is in scientific notation if it's in the form a times 10 to the power of m, where a is a number between 1 and 10. And then we have a power of 10, which goes nicely with our decimal system. So the three numbers shown here, 3.1 times 10 to the power of 6, 9.03 times 10 to the power of 4, and 2.5 times 10 to the power of negative 6, these are all expressed in scientific notation. The a value, that would be the numbers in front, 3.1, 9.03, or 2.5. These are all values between 1 and 10. And then we have powers of 10. Another thing I should say is that m is therefore going to be an integer value. It could be positive or negative, but they are whole numbers. If we have something like 12 times 10 to the power of, let's say, 3, that is not properly in scientific notation because 12 is not less than 10. And if I have something like 0.04 times 10 to the power of, let's just go with 3 again, this is also not in scientific notation because it has a value that is less than 1. In order to rectify this, I would consider, well, 12 would have to be divided by 10 to make it a number between 1 and 10. I can't just divide by 10 because that obviously changes the value. But if I multiply by 10, now all I've really done, divide by 10, multiply by 10, is multiply by 1. So this expression here is going to have the same overall value as the original expression. And this allows me to now express this as 1.2, oops, that should be a period, not a comma, times 10 to the power of 4. Likewise, if I wanted to convert the 0.04 times 10 to the power of 3 into a proper scientific notation, I would have to multiply 0.04 times 10 squared, times 100, which would turn it into 4. But I can't just multiply by 10 squared without dividing by 10 squared to keep things balanced so that I'm not changing the overall value. So this would then lead to me having 4 times 10 to the power of 1. I mean, obviously that's just the number 40, but in scientific notation, that would be 4 times 10 to the power of 1. How do I, we're just going to actually talk about what these mean. So 3.1 times 10 to the power of 6 is 3.1 times 10 to the power of 6, which is a million. So 3.1 times a million is 3,100,000. 9.03 times 10 to the power of 4, 9.03 times 10,000. So this is going to be 90,000 and 300. If I'm multiplying by 10 to the power of 6, this is essentially dividing by a million. So what this one is going to be equal to in sort of its full expanded form. My brain really wants to do commas today. So 0.0000025. I'm kind of looking at where the decimal place is relative to where it was in the scientific notation, and it is 6 places away from where it ends up in the expanded form. Likewise, in each of these other cases, if I consider I have a decimal point here, that is 4 places away from where it was in my original scientific notation, and in the 3.1 million, it is 6 decimal places away from where it was. Going the other way around then, obviously place values are important. For numbers that are very, very large, we're going to end up with scientific notations that have positive exponents of 10 because they're multiples being multiplied by 10. And for numbers that are very tiny, such as in the second example, we're going to have negative powers of 10. In the first case, I can ignore basically all the zeros. This is going to be 9.6 times 10 to the power of, and here's where I have to figure out how many place values I have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 10 to the power of 14. I essentially want to move the decimal place enough that I have one single digit, one non-zero digit, before the decimal. Likewise here, I'm going to have 8.34 as my a value, which means the decimal has to move to this location. How many times would it have to do that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is times 10 to the power of negative 15. And that is how you express numbers in scientific notation.